Hello everyone, and welcome back. So we're going to continue with the equivalent circuit of a transformer, and I just want to show you a few things quickly in this video. So in the last video we looked at this equivalent circuit of a transformer, and we looked at these shunt components over here, and we said no, we're going to take them out because they don't affect the calculations too much. So we said we'll remove those, and remember those was just the magnetizing current and the core losses, hysteresis, and eddy currents. So we said we would take those out, and then we ended up with an approximate circuit. So we call it an approximate circuit because it's not exactly correct because of those shunt components we're going to just ignore. And then it didn't look so bad. We just had the resistance of the primary, the leakage flux on the primary side, and we had the leakage flux on the secondary side, and the resistance of the secondary coil. And then we said to ourselves, we're going to shift the resistance on the secondary side, and we're going to shift it over to the primary side. And when it shifts over, R2 on this side is going to be R2 prime on this side, and then the leakage flux on the secondary side, X2, we're going to shift over to the primary side as well, and that's going to become X2 prime on the primary side. And then we could add those two together, and then we would have something like this. So we would have XE, which is X equivalent, and X equivalent equals to R1 plus R2 prime. So you add those two resistances together, and the same for the leakage reactance. XE is just X1 plus X2 prime. And the way we do this is obviously, if we just look back at this one, I can't just move this resistor over and move that inductor over, because the voltage on the primary side is different and the current is different on the primary side. So what we do is we just look at the power consumption. So let's just look at the resistor because that's easy. We just look at the power consumption of R2, and then we just make sure when we shift it over, even though the voltage and current is different, we make sure the power consumption is the same. The same for the inductor. So let's just look how we do that quickly. So what I've done here is I've written down the general equation for an ideal transformer. So like you guys did in 4, when you just had a primary voltage, a primary coil, and a secondary coil and a secondary voltage. So that was on the ideal transformer when there's no leakage flux, no resistance. So pretty much that kind of transformer doesn't exist. But you'll remember the equation: E1 over E2 equals V1 over V2 equals N1 over N2, and equals the inverse, current 2 over current 1. So remember, voltage is inversely proportional to the current. All right, so just remember that, and then we need to look at this over here: power. P equals I squared R. So that's the power equation that you guys know. Okay, so on the primary side, firstly, actually let's look at the secondary side. So if we look at the secondary side here, so we're looking at this resistor. Let me just move that up quickly. Yeah, this resistance over here now. So R2. So what is the power consumption of that? It's I2 squared times this resistance. Okay, so that's what I've got here on the secondary side: I2 squared times R2. Okay, now if I shift this resistor over, what will I have? I'll have, so on this side here, there's obviously I1, and when it's shifted over, it's going to be called R2 prime. So let's look at this quickly. So on the secondary side again, we have I2 squared times R2, and on the primary side, when we transfer it or refer it over, it's going to be I1 squared times R2 prime. And all we do with that then, and we equating the two because the power consumption has to be the same. So what we do is now is we just shift the I1 squared over, and we get I2 squared over I1 squared times R2. And I'm sure you'll agree with me that we can take the squared out and put it into brackets like that. So now we're left with R2 prime equals I2 over I1 in brackets squared times the original R2. All right, so I wrote that in red there. I don't know if you can see the I2 over I1. And if you just look up here at the ideal, the general equation for an ideal transformer, you'll see that there we have I2 over I1. And what we can do now is we can also, we can change I2 over I1 with V1 over V2, because that's also the same. And we can also change it with N1 over N2. So now we've got three different equations that we can use. So sometimes they might only give us the currents. They might give us the resistance of R2, and they might give us I2 and I1. And then to find out what R2 prime is, we can use one. And then sometimes they might give us the primary voltage and the secondary voltage. And then what we do is we can use this one. We'd use V1 over V2, and we use the voltage of R2. And then the same for the last one. Sometimes they'll just give us the turns of the primary and the secondary, and then we can just use this one. So here I just wrote on this side the equation again so you can see. So R equivalent equals R1 plus R2 prime, and that equals R1 plus R2 N1 over N2 squared. So that's that one there. And also so just remember now that the turns ratio, you can also change it with, you can replace it with V1 over V2, or you can replace it with I2 over I1. And then lastly, the leakage reactance, XE equivalent equals X1 plus X2 prime. So that's when we shifted the leakage reactance 2 over, and we can just like with the resistance, we can say XE equivalent equals X1 plus X2. So that's when it's on the secondary side, multiplied by N1 over N2 squared. And the same, we can also replace N1 over N2 with V1 over V2, or we can replace it with I2 over I1. So now we're going to look in the next video, we're going to look at a problem when we use this. And I'll see you later.